Well, welcome back. We are right on time. It's 11 o'clock, and we have the honor to have Dr. Shawn You to present the next section, and his topic is Introduction to Mechanical Hybrid Simulation. A lot of people know Shawn as a global expert. He has been working for MTS for 21 years, and his footprints are all over the places. I understand that right after today's presentation, he's heading to China for another full-blown of the seminar series with the critical customers. And Shawn has been in many, many different critical roles within our company, and he involved with so many different analysis, such as finite element analysis and the multi-body dynamic analysis. Not to mention the hybrid simulation with some visual and model assist simulation as well. And he has been working with several projects involving the R&D consultation with some critical projects with the partners. And he has been developing and implementing a lot of new test technologies with the customer requirements. And you've been with the hybrid simulation for more than 12 years, right? Become the expert of this area and set up dozens of the hybrid simulation systems around the world. A lot of them was the civil seismic, bridge construction, and the tall buildings simulation. And now he's getting into some aerospace, defense, military, and wind energy, wind blade testing, bearing testing as well. So let's welcome Dr. Shawn You for your topic and your session. Thank you.
Thank you, Garth. Today I will talk about hybrid simulation in general, overview, and the principle. So I will cover the MTS hybrid simulation solutions and hybrid simulation examples and the trend of hybrid simulation at that. So we know that in civil structure, in earthquake simulation, there are mainly three kinds of tests, three types. Shaker table test is widely used, and so the advantage of shaker table tests are accurate, and you can use an iterative approach and simulate the ground motion, and the ground motion can be simulated very accurately. And in that sense, it is very accurate. But the disadvantage is, the investment. You need to put a lot of money to buy the shaker table, to build the facility, and you need a lot of money to build the specimen, full-scale specimen or shrink-down specimen. And to operate the shaker tables takes a lot of money. It uses a lot of electricity, and so the shaker table test, ideally it is very accurate, but it costs a lot of money. So and another thing is, no matter how big the tables are, they are not big enough. And even the world biggest shaker table in Japan, this big, 15 by 12 meters, but it cannot hold a tall building, skyscraper. It's impossible. So people have to build a small scale specimen and shrink down the specimen, sometimes by a scale of 1 to 50. Then a lot of the details are lost, and the accuracy of the test is a question. So that's the shaker table test, but a lot of research institutes still do shaker table tests. Another kind of test is substructure pseudostatic test, and you do the cyclic type of loading and on a substructure like this, and actuators are very slow, and you are testing a component substructure, so the test is quite simple and doesn't cost a lot of money. But the thing is, the cyclic loading is not corresponding to the real earthquake loading, so the accuracy is a problem. And another type is hybrid simulation. So you build your model in FEA, and the FEA model part of the building structure, and the critical part, really nonlinear part, you cannot model accurately. You put it in the lab. So during the hybrid simulation, analysis model calculate the displacement at the connection point and send that command to the lab, and using lab actuators to load the substructure, and then the force feedback go back to FEA and calculate the next command. So this is a hybrid simulation. So it has a numerical substructure and a physical substructure. So it is more accurate than pure FEA because the hard-to-model component is tested. It is more accurate than the quasi-static test, and because the model provides the dynamic load time history. Yeah. So because of these reasons, hybrid simulation is a hot topic right now in civil structure, in other areas as well. And MTS has been involved in this hybrid simulation world for quite many years. And maybe starting from early 90s. So we contracted some researchers to develop our own hybrid simulation software. And after UC Berkeley developed the Open Fresco, so then we worked closely with the UC Berkeley and used their hybrid simulation and conducted a lot of hybrid simulation tests. And we developed our own solutions, and we offer our solutions to many of our customers in different world, different subjects, different areas. Yeah. And so we have helped many of our customers to learn hybrid simulation, to implement this solution. So over the years, we have provided over 100 hybrid simulation solutions to our customers, and including civil structure, ground vehicle, wind energy. So our hybrid simulation solution include quasi-static hybrid simulation or a slow hybrid simulation. So in some of the structures, for example, this bridge, and any element, and it should handle 3 load components. One is proportional to acceleration, inertial force, and another is proportional to damping, so damping force, and another is a stiffness term. So if the member is rate independent, then the test, the lab can only, can provide only the stiffness term. The inertial term and damping term can be included in the numerical model. So in that case, the lab, because only provides the stiffness term, and it can provide it fast or slow, depending upon what kind of test equipment you have. Then, then the requirement for the test equipment is reduced significantly. So you can use slow. So you can use slow actuators, and the hybrid test can take long. It doesn't matter because test only provide the stiffness term. So then our solution is, you have a FE computer here, simulation PC here, and then simulation generated command, and the command is sent to OpenFresco. That's the software developed by UC Berkeley, and then the OpenFresco software sends to another software that's MTS developed called the Computer Simulation Interface. So that software get the command from OpenFresco and map it to the controller software. So then that controller software sends the command to the controller, move the actuator, so the feedback goes back the same way. So this is our slow hybrid simulation solution. So the key part is the interfacing software, OpenFresco and CSI. Yeah. OpenFresco, like I said, is UC Berkeley software, and the CSI is MTS software. So OpenFresco is the software developed for hybrid simulation, and it connects to different analysis software like ANSYS, like OpenSeas, and so OpenSeas is also UC Berkeley developed finite element analysis software, and it is by far most widely used in civil structure for hybrid simulation. Yeah. So our customer, most of our customers use OpenSeas to do hybrid simulation. And so that's software. And for hardware, and you need actuator controller, definitely. But for slow hybrid simulation, quasi-static hybrid simulation, so the actuators do not need to be that fast. And for that reason, you can save a lot of money to buy slow actuator like this with a small servo valve. And also, this kind of actuators can be easily controlled, and so it couldn't do a lot of damage. And you do this kind of slow hybrid test, that technically is much easier to do. You don't need to do a lot of compensation because the loading is very slow. It is really easy to achieve the command you wanted. So, like I said, the middleware, the connection between the FE software and the test system, that middle software, one is OpenFresco, developed by Berkeley for hybrid simulation purpose, and another one is computer simulation interface, that's MTS software. So OpenFresco get the command from analysis software like OpenSeas, and then so the middle part is OpenFresco. It does the transformation and output the command in the format that MTS software can accept. And then CSI, that's MTS software, get the command and map it to the proper channels in the controller. And then OpenFresco need the feedback in certain order, then CSI provides exactly the same signal in same order, and then feed it back to OpenFresco, then feedback to the analysis software, and solving for next step. So that's the software structure for slow hybrid simulation we provide. And the majority of our customers do this kind of slow hybrid simulation. And for the finite element analysis software, like I mentioned, OpenSea definitely is the most widely used finite element analysis software so far for hybrid simulation in civil structure. But OpenFresco can connect to all kinds of finite element analysis software, like Abacus, like LS Steiner, like MATLAB, Simulink, ANSYS, so all this. So as long as the FEA package has a user-defined element function, then theoretically that package can be connected to OpenFresco and it can be connected to CSI, can do hybrid simulation. Yeah. So that's our slow hybrid simulation. So we also provide real-time hybrid simulation. So real-time hybrid simulation means, the real event is how long, and then the hybrid simulation got to be the same time, finish in same time. In this case, the test provides all these three terms: inertial terms, damping force, and stiffness force. For example, in this case, and this is a very tall building, and we are studying the mid-level isolation, and so the test specimen is a mid-section of this building, and then the analysis part can provide information of the bottom part and the top part, and the boundary condition is calculated by the FEA and applied to this shaker table. And the top boundary condition is also calculated by FEA and applied by, say, actuator. So this is got to be real-time hybrid simulation because this is an inertial reacted test, and you got to model the acceleration, apply the acceleration in real time. Able to load the midsection accurately. So this is a real-time hybrid simulation example. So in real-time hybrid simulation, so we have our solution like this. So the model got to be built in Simulink, MATLAB Simulink, and then the model got to be compiled to a special computer called the target PC. So the model is converted to C++ code and running in this kind of a target PC. And this target PC has a very simple operating system, not like Windows, and so it is very efficient, not a lot of overhead, so the model can be solved really fast. And then there's a chance you can catch the real time. And also, the command can be sent to the controller really fast, so and store really fast. So we use a SPAMnet card to store the command, use a fiber optic cable to transfer the command to the controller, and then use a fast actuator to realize the command in real time. So the model is solved fast, store fast, transfer fast, so there's a chance you can do the real-time hybrid simulation. Still, the model cannot be very complicated, and if it's too complicated, and the model, even in target PC, cannot be solved really fast. So in real-time hybrid simulation, again, you got to have a controller. Controller got to have a square net card installed inside, and so we have a different controller type. Yeah. And the actuator got to get the command from the square net card in real time. And so, like I said, in this real-time hybrid simulation solution, and we require the model to be created in Simulink environment. So that's hard. And considering you create a Simulink model in FEA model in Simulink, and it's so far not a lot of software package you can use to create your FEA package in Simulink environment. So the model is hard to create, and also because the controller rate is fast. Every millisecond it needs a command. So the model got to be solved every milliseconds. So every millisecond you got to solve the FEA model. So FEA model got to be very, very, very simple. So the models got to be very simple, and it's really difficult to create these models. So those are the bottlenecks for real-time hybrid simulation. For that reason, and we also provide another solution called soft real-time hybrid simulation. So the soft real-time is just like real-time, except the analysis software is not limited to Simulink. You can use OpenSeas, you can use others. For example, you use OpenSeas. That's non-real-time FEA package, and it solves for the command, and the command is sent through OpenFresco to a target PC. So in here, it runs a program called a predictor corrector developed by UC Berkeley. So it allows the controller rate and the FEA solving rate to be different. The controller rate, for example, 1 millisecond, it needs a command, so that's the controller rate. FEA solver doesn't need to solve it with that fine step, so could be 10 milliseconds per step. So then in between, this predictor corrector and predicts the command, and before if the solver, FEA solver, couldn't provide the command in time, and so it predicts until the model is solved. Then this predictor corrector goes to correct mode, and from predicted command to the calculated command. So it goes to prediction mode, correction mode, and in that case, the model can be solved with much larger steps, allowing more time for FEA model to be solved. Then the model can be more complicated. So this is our soft real-time hybrid simulation solution. So to do hybrid simulation test, especially real-time or soft real-time, there are many challenges. and stability issue and convergence issue. And so before you do your real hybrid simulation, our suggestion is you have to do the simulation first. And you have to use software to simulate your specimen. And then here's your main hybrid simulation program, and then here's the simulated specimen, and then you use open fresco and other method to simulate your real hybrid test. So we have different methods, and I believe later on we will talk in more detail about this virtual hybrid test. Yeah. So, and also, so we talk about use open fresco to do this virtual hybrid test. So, so in here, this is your main program probably in OpenSeas, and then you have a virtual specimen, virtual test system. You can use other software like ANSYS, Abacus, or OpenSeas to simulate your specimen, real specimen. And the connection in between, you can use OpenSeas, you open fresco to connect the two parts. Also, in flag test in our controller software, and we have a calculation channel function. Later, we will introduce more detail. And then in using this function, you can simulate your specimen in very detailed fashion. And then in this case, you can simulate your hybrid test. And this part, the real test part, you can use the calculation channel and model this specimen and the test rig. And so this is an example for virtual hybrid test using a calculation channel. Yeah. So there are many functions. And also in real time hybrid test, and you got to be careful because in the real hydraulic system and the command and the feedback, there's always a delay between 15 milliseconds to maybe 60 milliseconds delay. So this delay in regular test doesn't matter that much. But for the hybrid simulation, this delay is equivalent to a negative damping. So then, if this negative damping is more than the system damping, and then the hybrid test will go unstable. So you have to compensate for this delay. And there are different methods, and we provide different delay compensation method, like this adaptive feed-forward compensator, and it automatically learn and find out the delay, the error between the command and feedback, automatically adjust some of the parameters in this compensator, and then so that the delay is compensated, so that the roll-off error is compensated. So in this case, the hybrid tester will be stable, and the hybrid tester will be accurate, because you have this delay compensator to make sure the delay is not much, make sure the roll-off error is not much. Yeah. So, and next I'm going to talk about some hybrid test examples. So this example was done by Dmitry Lagnos while he was at Stanford University. And he worked with some UC Berkeley people like Andreas Schellenberg on this example. So this research is to find a retrofit solution for some old building and to make the old building stronger, so more earthquake resistance. So they designed some kind of a panel, energy absorption panel like this. And so they want to test whether the panel, if installed in a building, old building like this, whether it will improve the earthquake resistance. So that's the purpose of this hybrid test. So in this hybrid test, so the panels are the experimental substructure and tested in the lab, I think at UC Berkeley. And the old building was modeled by OpenSeas. And so you can change the building structure or whatever, and really easily, and then coupled with the test specimen with the open fresco. Yeah. So in this case, they can study this kind of a panel and its effect to all kinds of building, because it's really easy to create a ANSYS model or OpenSys model to model the different buildings. Yeah. So in this test, so like I mentioned, the old building is modeled in OpenSys, and the connection used open fresco connect to the experimental element, the panel structure. Yeah. So using this hybrid test, they found out that they designed the panel and found out that the panel really is effective to increase the earthquake resilience for the old building. And they could evaluate the design and easily coupled with all kinds of existing buildings, and really reduced a lot of cost, because the building structure is all in OpenSys. And in this way, they can really design the panel structure really effectively with a relatively low cost. Yeah. So this is an example of a hybrid simulation, and it is it's effectiveness. So next, I'm going to talk about hybrid simulation trend. So we see a clear trend is to couple the shaker table test and use the shaker table to do the hybrid simulation test. So before, and the hybrid shaker table test mostly test the full structure. If the table is not big enough, then you have to shrink down the whole specimen, shrink it down to a factor of maybe 10 or 50 or something like that. But with the hybrid simulation, and the shaker table can test part of the structure, like early on, Khalid Masalam's example, and tested the electric switch, and they only tested a part of the structure with a shaker table. Then the scale of the test reduced a lot, the difficulties reduced a lot, and they saved a lot of money. So we saw that, we see that trend, and a lot of researchers and wants to do mid-level isolation, and then the building, the top building is tested on a shaker table. The bottom portion is analyzed. A lot of researchers want to do this, and so the shaker table test is coupled with analysis model, probably through open frescoes. Yeah. So the idea was first provided by UC Berkeley, Steve Mahan. So this picture was provided by Steve Mahan. And so this is an example we did at Tongji University. So MTS and UC Berkeley and Tongji University, we formed a team and conducted this test. So in this test, the shake table is at the bottom, and the bridge deck is on the top. In between, there's a isolation, elastic isolation material, bearing material. So the foundation, the columns are all in the analysis model, and the isolation bridge deck is on the shaker table on the shaker table. So this is a shaker table, using shaker table to do real-time hybrid simulation. Yeah. And also there's another trend to use to couple the shaker table and the loading actuator to do hybrid simulation. So for example, you use you want to do mid-level hybrid isolation study, but this building is connected to another building in some way. And then you can use an analysis model to model the lower portion of the building and adjacent structure, and then the interaction can be applied by an actuator. And so in this case, the shaker table, actuator, they all coupled with the analysis model. Yeah. So through the connection, you could use open fresco. Yeah. Again, this picture, this diagram was provided by Steve Mahan of UC Berkeley. So this is another example. We did, again, same project. MTS and UC Berkeley and Tongji, we worked together at Tongji University. So again, this shaker table, and now the column is here, the columns are here, but the weight on the bridge deck is missing. So the inertial force due to the weight was provided by analysis model, sent to this actuator, and applied it in the real time. So, so the numerical substructure includes the foundation and then the weight on top. So everything in the middle is the experimental element and tested in the lab. So that's the experimental element tested in the lab, and the weight is on top, and the inertial force caused by the weight is applied by this actuator. Yeah. So this is a typical shaker table coupled with loading actuator hybrid test, real-time hybrid test, yeah, at Tongji University. So. And we used the delay compensation method and the feed-forward compensator and adaptive. And then you can see the command follows feedback so accurately. There's no delay. The test is stable. Yeah. So we see another trend is to use a multi-DUF control system to do hybrid simulation. And what is the degree of freedom control? So degree of freedom control is like this. So if you have a control point, you want to control this point, and X and Y. If you have an actuator, two actuators like this, and one moving, one does not, then it goes to an arc. So globally, it is not controlling XY displacement accurately. It's controlling an arc. And degree of freedom control means you control the motion or force in global coordinate system accurately, and there's no cross-coupling effect. So, for example, this mast and also the Swinburne University, the mast, it has a degree of freedom control software. It has 8 actuators and controlling 6 degree of freedom in global coordinate system. XYZ translation and XYZ rotation. Yeah. So this DOF control software can automatically conduct the coordinate transformation, and if you want the SIG DOF at a certain location, it automatically transfer it to the actuator coordinate system and move the actuator accordingly to achieve the 6 DOF in global coordinate system in real time. Yeah. So this is a degree of freedom control software. And for example, so this is another interesting system at the Sichuan Highway Research Institute. And so they have 6 actuators control any point, global 6 DOF in global coordinate system, in force control or displacement control or mixed control. So they use our DOF control software to achieve that. And that coupled with hybrid simulation, and so that's going to be very effective tool. So this is a eco-polytechnic system, 6 DOF control software, and also there are many 4 DOF control software, and this is another 4 DOF system, and can be easily achieved by our DOF control software. Yeah. So another trend is hybrid simulation. Now, it started in civil structure, but now it's migrated to all other different areas. So this is a ground vehicle application. Later on, I will talk more. And this is a wind energy application at a DTU, and blade test and hybrid simulation with ANSYS, and later on I will talk more. So this is an aerospace application, and hybrid simulation application only test a damper and model the rest of the helicopter system. So in conclusion, so hybrid simulation model part of the structure and then test a part of the structure. So it is more accurate than pure analysis because the hard to model component is tested. And it is more accurate than the quasi-static substructure testing because the loading is provided by FEA. It models the real earthquake. Yeah. So MTS has been in this area for close to 20 years, and we work closely with the leaders like UC Berkeley, like Tongji University, like other universities. And we have our solutions, quasi-static hybrid simulation, real-time hybrid simulation, soft real-time hybrid simulation, and we want to help our customers to implement those solutions, and we want you guys to be successful in hybrid simulation. Not only in civil structure, but in aerospace, wind energy, ground vehicle, yeah, any other, anything you are working on. Yeah. So that's my presentation, and any questions? Yeah.
How does this open seed software compare with the commercially available like ANSYS or others?
Okay. OpenSea's FEA software is tailored to civil structure hybrid simulation. It's a NIST-funded project, and they gave the money to UC Berkeley, and UC Berkeley developed this package. So it is not so user-friendly like ANSYS and Abacus, and ANSYS, Abacus. You can create fancy meshes and shell elements and beam elements, so many kinds. And OpenSea's, by far, the pre-processor is not that user-friendly, and the element types are not that many, and the support definitely cannot match up with ANSYS and Abacus, but it is tailored for civil structure. And a lot of material like concrete and OpenSeas has, and others maybe do not have. And shell element, there are a couple, not many, and solid element, there are a couple, not many, and so you can build complicated models, but not that not as easy as ANSYS. So, yeah. But the biggest advantage is free software.
Yes.
Yeah. So.
Thanks.
Yeah.
The accuracy of hybrid simulation is depend on your FEM model.
Correct. And also
So
the
how you
the
can
test.
say quasi-static test is not accuracy?
Yeah.
But because it's FEM, anyone can do different
Yeah.
accuracy.
Yeah.
So you can't say like hybrid simulation solution is accuracy greater than or better, like compared to quasi-statics. It's best. You can't say like that because of its FEM, depend on FEM.
So the accuracy of hybrid simulation is a bigger research topic, and definitely it requires the numerical part to be accurate and the test part to be accurate as well. So if the numerical part or test part is not that accurate, and then it could be converted to totally different places. So many times, hybrid test, especially at the very beginning, and yield some weird effects. And so you got to debug your model and make sure your model is accurate. Make sure your test is accurate. And that's why the virtual testing is so important. So we first do the pure FEA. Then pure FEA we compare to theoretical solution or whatever, and we make sure the pure FEA we trust that. Then we take the test element, and then we model that test element with another package with another model. So then this is a virtual hybrid simulation. And then we can control the virtual specimen, and then the virtual hybrid simulation matched with FEA, and then we say, okay, virtual hybrid simulation is right, the model is right. Then we replace the virtual specimen with the real substructure. Then compare that result, and we say, okay, it matches up fairly good until the nonlinear region. Then we have more confident. So.
One other question.
Yes.
Between the load control and displacement control when do the testing and input?
That's a really good question. And so far, The hybrid simulation tests we do are all displacement control. So, but because we want to use the method to aerospace and other industry, and sometimes the specimen is very rigid and displacement is really tiny, so we got to use force control. So we are developing the force control hybrid simulation solution now, and hopefully pretty soon it's going to be available. Yeah.
Thanks for that.
Yeah.
Thank you very much, Dr. Shawn You.